Okay, so in example 1, we have a bacteria culture starting with 2,000 bacteria, and after 3 hours, the estimated count is 10,000 bacteria. The growth is proportional to its size. That last statement is important, so we know that these are the types of questions we're doing. And these are the only ones we're going to do this year, so don't panic. It's not like ones like last year where the growth had a half-life or a doubling time. Here, the growth is proportional to its size, so we know where you're going to use the E function. Okay. So find the bacteria after T hours. So this is like find the formula that we can use to answer any follow-up question. So the general formula we're going to use is y equals CE to the KT, but we want it specific for this scenario. So let's start filling in information we know. So we know the C. C is the initial value, which hopefully you can see is 2,000. What else do we know? Well, we know the T part. The T is after 3 hours. Well, at least in this snapshot, T is eventually going to be just blank, but in this snapshot, we're going to use the 3. And we also know that the count right now, after 3 hours, is 10,000. So Y is 10,000. What's missing, and probably the most important part of this formula, is the K. And so what we do here is we use this snapshot to get our proportional constant K. So the scenario is actually talking about you start with 2,000 and it grows proportional to its size. We just happen to know a snapshot in time. So we know at 3 hours, this is how much we have. So because we know that snapshot, we know where it started, and we know where we are 3 hours from now, we can use that snapshot to get that proportional constant. Excuse me. That proportional constant can be different in every question because the way it grows is different. But at least here we have that snapshot of the 3 hour mark, and we use that snapshot to get K. So let's plug in our information. Y is 10,000, C is 2,000, E to the K times 3. And what we have to do is solve for K. Now this is not unusual. We've had questions like this before where we want to get to the K, get to that exponent. First we got to get rid of the 2,000, right? We got to divide both sides by 2,000. So that's going to be 5 equals E to the 3K. I'll just write it like that now. And now this becomes just like the other questions we answered last semester. We have to get at that exponent. Well, the way we get at it is through logarithms, because logarithms will allow us to bring that exponent down. But we're not just going to use any logarithm, we're going to use the natural logarithm. So we're going to use lns. So we'll, instead of taking the log of both sides, we're going to take the ln of both sides. Why? Because we're using e. So it's ln e to the 3k. Regardless, this is still a logarithm. So all the logarithm rules from before apply, which means we can take, since we're taking the log or ln of some exponent, that exponent can come out front. And we can just get the ln e. This is going to stay the same. That's the whole reason we take logarithms, that it gains us access to that exponent. And the reason we didn't just do any logarithm is because we're dealing with e, and it makes this little scenario great. Ln e means what exponent do you put on e to get e? So we know that that's 1. So it makes our question even easier. We just have 3k equals ln 5. Divide both sides by 3. Ln 5 divided by 3 equals k. And that is our proportional constant. However, I'm going to write it a little differently. Instead of dividing by 3, I'm going to multiply by 1/3. It just looks a little bit nicer for me. And that is our proportional constant for this particular growth. And we can now use, once we know that proportional constant, we can use it to answer, find out how many bacteria at any time, or if we have the bacteria known, we can figure out how long it's taken to get here. So now we can take that and plug that into our formula and say it's y equals 2,000. Let's just come back so we can see it. So the 2,000 is going to stay the same regardless. E to the k, and our k we just figured out is this number, 1/3 ln 5. Remember, it's just a number. T. I know we know t in this scenario, but we want to get an equation for t that we can use for any time. And so we found our formula after t hours. So this is a proportional exponential growth specific to this scenario, but now we can answer any question about the growth, including something like this. Okay, so I know the number of bacteria after 3 hours. How many bacteria were there after 2 hours? So we'll use our formula that we just had, y equals 2,000 e to the proportional constant of 1/3 ln 5 t, except we're going to sub in t equals 2. And now we got to figure out why. Well, this is now all an exercise just on your calculator. Because if you look here, there are no variables anymore on the right-hand side. Those are all numbers. So now you just got to go off and punch this in your calculator. Now we know every calculator works a little differently, but a strategy when punching in your calculator is to try and do all this exponent stuff first. So I would punch in the ln 5 first, divide by 3, then multiply it by 2, get all this big long decimal, then push the e to the x button or put in e to that answer. Then go off and multiply by 2,000. I'll show you how I do it on the graphing calculator. It may be a little bit different on your calculator, but it'll at least give you an idea. So like I said, I'm going to work in the inside, so I'm going to do ln 5 first. Ln 5. Get an answer. Then I'm going to multiply it by 1/3, or the same as divide by 3. Then I'm going to multiply it by the 2. There's my big exponent. So that's all of this. So now it's e to that exponent. Now, on some of your calculators, you can just push the e to the x button and it will do that. For me, I have to type the e to the x and then type in that whole long answer. Instead of that, I'm going to actually use my little answer button. So it's e to the power of that at 2.92. That now gives me all of this. And I just got to now multiply it by 2,000. And I will get a final answer of 5,848 bacteria. I'm not going to put a decimal bacteria there. It doesn't make sense. So I'll round it to the nearest whole bacteria. Again, your operations on your calculator are going to be a little bit different. That's why I'm not going to write any steps down here. You're just going to go off and punch all that in your calculator to get your answer. So that's great. But what else we can do here is start asking some calculus, because we haven't really used any calculus yet. So instead of asking the exact number of bacteria at 2 hours, I'm now curious about how fast it is growing at 2 hours. So the rate of change, the rate of growth at 2 hours. I know there's whatever, 5,800 bacteria there at 2 hours, but how fast is it growing then? That's the calculus. So I know that the rate of change is the slope of the tangent, which is all the derivative. So we have our function which describes how many bacteria are there. So 2,000 e to the 1/3 ln 5 to the t. But if I want to know how fast it's going, I'm going to differentiate it and find y prime. So the good news is this is really just a single e function. It has a coefficient and it has an exponent. The derivative of any e function, the coefficient stays the same. And the derivative of the e function is itself, so everything looks the same, times the derivative of the exponent. And the exponent itself is actually just a little t value, something to the t, or something t. It's not quite 6t or 7t. If it was 7t, the derivative would be 7. But it's not 7, it's another number. It's 1/3 ln 5t. So the derivative of 7t is 7, so the derivative of 1/3 ln 5t is 1/3 ln 5. So that is the function that describes how fast the bacteria is growing. And we don't want the entire derivative, we want the specific time at t equals 2. So we go off and go y prime at 2. So wherever the t is, we put in a 2. So it's e to the 1/3 ln 5 at 2 hours times 1/3 ln 5. And again, this is an exercise on your calculator. If you'd like to watch me punch it in my calculator, I could do that. Again, I'm going to work from the inside out here, so I'm going to start with the ln 5. Get an answer, divide by 3, get an answer, times 2, get an answer. I'm going to go e to that power. Get an answer. So I've figured out all of this part. I think now I'll multiply it by 2,000. So now I've got this part. Now I've got to multiply it by this. I think I'll first multiply it by ln 5. So times ln 5. And then I'm going to multiply it by 1/3, which is the same as dividing by 3. And I get that the answer is 3,137. Now remember, it's not 3,137 bacteria, because we know at 2 hours there's 5,800 bacteria. This is 3,137 bacteria per hour. That's how fast it is growing. So at 2 hours, that's how fast it is growing. And the reason it's per hour is because the question had hours in it. If it was minutes, it would be obviously something else. And the last one, not calculus, just going backwards now. If I said, here is the what's the population, or when is the population 1,800? So using the same original equation that we solved, except now instead of subbing in a time, we're going to sub in a value. So we're going to sub in 18,000 in for y. I'm going to do this relatively quickly because this video is getting pretty long and we might run out of data space, so we're going to go off. Again, we need to solve for t this time, which we're going to have to isolate. We'll isolate, as always, by dividing by 2,000. That's going to get us 9 equals e to the 1/3 ln 5t. We're going to do the same thing we did before, take the log of both sides, but since it's e, we're going to be more specific and take the ln of both sides. By taking the ln, it gains us access to that exponent because the exponent will come down. Okay, so that whole exponent here came down out front, and it left us with a ln E. As always, ln E is what exponent do we put on E to get E, so it's 1. So that leaves us with this. And I need T by itself, so I'm going to divide by that. Okay, and again, this is an exercise in your calculator. Tricky part is dividing by 1/3. You could, if you wanted, instead of dividing by 1/3, have it multiplied by 3 on the top. I'll let you figure out how to work your calculator, but I get an answer of 0.096, which means that the answer is about 4.1 hours. So that shouldn't be a surprise. You know, this is 18,000 bacteria. We saw at 2 hours that we're only at 5,800. So this is a lot longer. To get to 18,000, we're at about the 4-hour mark. So we'll pause here while you have a chance to either copy or get caught up, or copy down example 2.